So now we have this as our assumption. Okay, so from this we got this as the assumption. So under this assumption, we now show how to break the PRG phi. What does it mean to say break the PRG? Essentially what it means is that, so the pseudorandom generator takes a string of length k and produces a string of length 2k. So basically if I am given a string of length 2k, I have to decide whether it is coming from a truly random distribution or it is coming from this distribution. Okay, that is, given a z belonging to 0 1 to the power 2k, we need to decide if z is of the form, if z is a random string of length 2k, or z is of the form phi 0 y, phi 1 y for a y, a random y of length k. So we have to distinguish between these two choices. Okay, so how do we distinguish? So to distinguish between these two, we will define a function f. Okay, so we define a function as follows. Okay, what we do is, on input x, okay, let tau be the maximal initial segment of x. Okay, so I look at the tree ti and well, whatever x is going, let tau be the maximal initial segment of x that is a node in ti. Okay, so look at the part. Okay, so I mean if I just try to trace x, tau is basically the point till which I am able to stay inside ti. Okay, and let the length of tau be some r. So if tau is not equal, sorry, tau over here, right? Yeah. So if tau is not equal to sigma, that is, well, it went off, it branched off from here, the path leading to sigma at some point, then I will define f of x to be phi xn composed with phi x r plus 1 of y. So just one point over here that I want to emphasize is that the choice of this y actually depends on the node of the tree. Okay, so when we are saying that I choose a y randomly, it is for a node. Okay, so once I have a node of a tree, it is with respect to that node over there. Okay, okay. So fx is defined in this way, and if so again, so once again it's the first digit of this, so the first bit of this string, and if tau equal to sigma, okay, so basically let's say that it went to this node and then it went ahead, then what we do is that fx is equal to first bit of phi xn composed with phi x r plus 2. So basically I go one more level down over here, and now I take the left half of z if x r plus 1 is equal to 0, and it is equal to the first bit of phi xn phi x r plus 2 right half of z if x r plus 1 is 1. Okay. So basically the other case, if r plus 1 is 1, then I take the right half, and if r plus 1 is 0, I take the left half of z. Okay. So now let's try to analyze, and this is the definition of my function f. So now how is this function able to distinguish between the two? So now note the following. So if z is of the form phi 0 y phi 1 y, right? Then what is f? So there are two things for f, if tau is not equal to sigma and tau equal to sigma. So look at the first part. If tau not equal to sigma, then f is basically the same as what was the notation? So psi I of y, or psi r of y in this case, sorry, psi I of y, right. So it is basically the same as that. And if tau equal to sigma, okay, what is the left half of z in this case? So the left half of z depends on this bit, so x r plus 1. What is the left half of z if x r plus 1 is 0? So it is basically this. And if the next bit, if x r plus 1 is 1, it is basically this. Okay, so if z is this, then f is essentially drawn from the distribution psi I of y. Okay, so that is f of x is equal to the first bit of phi xn up to phi r plus 1 of y over here. Okay. Now, if z is, let's say, a random string in 0 1 to the power 2k, okay, in this case note that this does not have any significance, right? Because well, y is a random string and this part actually does not depend on z at all. But the part that is dependent on z is the second part, that is when tau equal to sigma. And here, because z is a random string, both the left and the right part are essentially just a random string, right? So therefore, this is basically going up to tau r plus 2. Okay, so if you the tree got erased over there, but essentially this is corresponding to the tree ti plus 1, the distribution that we got from ti plus 1. Okay, so therefore, if z is a random string over here, then f is drawn from the distribution psi I plus 1 y. Okay. And well, this distribution corresponds to the tree ti, and this corresponds to the tree ti plus 1. So therefore, what we have, so our assumption is that we can actually, there is an algorithm which is able to distinguish between these two distributions. Okay, so therefore we can distinguish between the two choices for z with probability at least 2 to the power minus order n by a polytime algorithm. Okay, so therefore it means that h phi is at most 2 to the power order n, right? So this is polynomial time, and this is just 1 over m, which is 2 to the power order n. Okay. So this completes the proof of this. So essentially the idea is, I mean the intuition here is that we are assuming that we can break a pseudo-random function generator. There is an algorithm which is able to distinguish between two functions, one a truly random function, another drawn from a specific distribution, and then using that we are able to show that if we start off with a PRG, we can able to distinguish between a string that the PRG generates versus a string that is truly random. Okay. So yeah, so this completes the proof and also the last topic of this course. So any questions? It's not a natural proof, because if that was a natural proof, yeah, it wouldn't have implied anything, but no, that's not a natural proof. Okay, so just to give a quick recap of whatever we have seen in this course. So we started off with this lower bounds on circuit size. So essentially we saw Shannon's lower bound, that is there are a large number of circuits which have circuit size at least 2 to the power n by n. Then we saw Shannon-Riordan's theorem, which gives a similar type of lower bound but a little stronger lower bound for formula size. Okay. Then we saw that well, if we look at formulas over the De Morgan basis, then by Kravchenko we get even better lower bound. We saw Nechiporok's theorem, which essentially showed that we can actually give a lower bound for a formula in terms of its sub formula or sub function. If I take a function, I can give a lower bound for this function in terms of the sub function. Then we saw Subotovskaya's theorem. So Subotovskaya's theorem, once again, it gave a connection between, so suppose if I have a function and I look at a random restriction of this function, so what is the or what is the connection between a depth lower bound for the original function versus the depth lower bound for this restricted function? So that connection was given by Subotovskaya's theorem. Then what else? Then we moved on to some constructions, some upper bound result. We saw that what did we do next? We can give a monotone, a polynomial sized monotone circuit family for majority. Okay, essentially Valiant's construction. And then we moved on to various arithmetic operations. We saw that if you look at addition, we can start by very simple construction of getting a order n depth circuit, which can be improved to order log n depth circuit with n square size, and that can even be improved further to the most optimal case, that is log n depth and linear size. Okay. Then we saw for division, we saw that we can get division in NC1 due to this famous result by Beam, Cook and Hoover. What else? So after that yeah, so after that we move to lower bounds once again, and we saw the monotone lower bound for click due to Rasborough. Okay, so if you look at the click function, and suppose since click is a monotone function, if you look at a monotone circuit for click, what can we say about its size? Okay, and then we argued that, well, the size, the monotone, I mean, if you have a monotone circuit for click, then it would require size that is exponential. Okay, Then we saw Rasborov-Smolensky's result for lower bounds on mod k function. Okay, so for any mod k, if you want to have ACC0 Q circuit, okay, where Q is some other prime and K is, let's say, some prime, then it requires not just super polynomial, but in fact exponential size. That is one way of showing that parity is not in AC0. And then we saw Hastad's result, which is another way of showing parity is not in AC0 by using the switching lemma. So Rasborov-Smolensky was based on this polynomial approximation of AC0 circuits, or polynomial approximation of gates essentially, which led to approximation of the circuit. And after that we moved to branching programs and saw that well, NC1 can be actually characterized as in terms of branching programs as well, more specifically branching programs of width 5 and polynomial size. And if we come down to width 3, then that corresponds to a very specific family of circuits, namely this what was it, mod 3 composed with mod 2 circuits. Okay, just depth 2 circuits that have a mod 3 gate at the top followed by mod 2 and then inputs below it. We also saw connection between communication complexity of a function and the circuit size of that function. So what does it mean to say that, I mean, how can I get a lower bound for a function if I know its communication complexity and vice versa. And finally, we saw that well, these various lower bound techniques for proving lower bounds for circuits essentially do not suffice if we want to separate NP from P/poly, okay, which is kind of the holy grail of circuit complexity, to show that if I take an NP complete problem, I cannot do it, I cannot compute it using poly-size circuit. So all these various results kind of led researchers to believe that probably we can separate NP from P/poly, if not NP from P. But this natural proof barrier due to Rasborov and Rudic kind of showed that any natural proof will most likely not work. Okay. So that is a very brief overview of what we have done. That can definitely work, yeah, those methods can work. But the point was that at that point in that 1980s, early 90s, all the circuit lower bounds that were there were actually exploiting this natural proof. Okay, so essentially it showed that if you take a function, you take a hard function, then that function satisfies a certain property, but any function that is computable by that class does not satisfy that property. Therefore, that function is not in that class. That was essentially the idea of showing lower bound. But now if that property is a natural property, then we showed that most probably that will not work for NP versus P/poly. And all those properties indeed were natural properties. That is what has been shown. So we did not get into that part, but that was shown in the paper by Rasborov and Rudic as well. I mean, in none of the non-trivial classes. Well, you can argue it is not in AC0. Parity is not in AC0, but nothing non-trivial. Not even in ACC0. You can't even say that if you take a function from NP, it cannot be solved by a bounded depth circuit which has arbitrary mod gates. NC1 also nothing is known, because ACC0 is contained in NC1. Any mod can be simulated by log depth. So nothing is known with respect to NC1 as well. Okay. Okay. So we'll stop here.